In this lecture, I will go through document clustering algorithms. For example, k-means clustering algorithms and its variations, hierarchical clustering algorithms, for example, agglomerative hierarchical clustering algorithms, single link, complete link, and group link, and divisive hierarchical clustering algorithms. K-means clustering algorithms. Actually, k-means clustering algorithms uses is a method which already partition the n points or n observations into k clusters, in which each observations belong to the cluster with the nearest mean. For example, suppose we have these many points, and suppose these are the clusters, then according to the definition of k-means, all points will show maximum similarity or least distance from its cluster center or mean. To achieve the k-means clustering algorithm, we can apply the following algorithmic steps. For example, suppose these are the points and we want to identify two clusters. Then first we will take two random mean points. Suppose the first mean point is this, represented as C1, and second mean point is this, represented as C2. And after that we will calculate the distance of these mean points with respect to all other points given in the plane. Similarly, we calculate the distance of all other points from cluster center C2 and then check which points are nearest to C1 and which points show minimum distance with C2. We assign all points which shows minimum distance with C1 and minimum distance with C2 as an initial cluster. So there will be two clusters, C1 and C2. And after that, for example, this will clear from first step. Place k points, here k is equal to 2 points, into the space represented by the objects that are being clusters. These points represent initial group centroids. Now assign each object to the groups that has the closest centroid. So this is the initial assigning. When all objects have been assigned, recalculate the position of the k centroid. Now suppose this is not a cluster center, actual cluster, so we will calculate again the centroid. So now the new calculated centroid is this, new calculate C1n and C2n. Now we will repeat the same process given in 2 and 3 until our position of centroid will become stable, or centroid no longer move. This produces the separation of objects into group from which the metric to be minimized can be calculated. For example, here two clusters C1 and C2 calculated by using this way. The complexity. Regarding the computational complexity, the k-mean clustering problem for observation in d dimension is it is NP hard in general Euclidean space D even for two clusters. NP hard for general number of clusters K even in the plane for d dimension. And if K and D are fixed, the problem can be exactly solved in time big O of n into d into k plus 1 log n time, where n is the number of entities to be clustered. Now this is an example of k-means clustering. Now the problem is we have total 8 points. Each point represents x coordinate and y coordinate. For example, this is x coordinate, y coordinate, point A1, and we need to cluster we need 3 clusters from these 8 points. So first we assign 3 initial clusters randomly. We take this as a cluster centroid of cluster 1, A4 as a cluster centroid of cluster 2, A7 as a cluster centroid of cluster 3. Now here we will calculate the distance between 2 points A and B. It can be calculated by using mod of x2 minus x1 plus mod of y2 minus y1, means difference of y coordinate, x coordinate plus difference of y coordinate. So now in this table it is clear, very clear. So this is the first cluster mean, represented distance mean 1, second cluster mean and third cluster mean. So I will calculate the distance of point A1 with respect to all 3 cluster means. Again calculate the distance of this point by using same method with respect to this and this cluster mean, and we will fill the entire table. So this is a simple calculation. The distance between here, this is an example of calculation of distance between point x1 y1 210 and 210 and mean x2 y2 58. So here x2 is 5, x1 is 2, y2 is 8, y1 is 10. So the distance is 5. This way we will fill the entire table. So this is the entire table. Now we will check the distance of all points with respect to mean. Now it is clear that point A2 shows least distance with cluster mean 3. So it will go to the cluster 3. Similarly, point A3 shows least distance with cluster mean 2. So it will go to the cluster 2 and so on. Now based on this categorization, cluster 1 will contain only 1 point, 2 and 10. Cluster 2 will contain total 5 points, and cluster 3 will contains 2 points, 2, 5 and 1, 2. Now the next step is, actually cluster 1 contains only 1 point, so we will not use this cluster to calculate another mean. We will consider this as a cluster mean for next iteration. But for cluster 2 it contains total 5 points, so we will calculate the new mean for this cluster. The new mean will be the mean of all x coordinates and mean of all y coordinates. Here it is calculated, and this is 6 and 6. Similarly, mean of all x coordinates and mean of all y coordinates calculated here, and this is 1.5 and 3.5. So after that we will again repeat the same process. We will put this mean here, this mean here, and this mean here, and again recalculate the distance and adjust and identify the new clusters. And then, for example, this is the step 1, this is step 2, this is step 3, and so on. And after that, this is the final set of clusters after third iteration. This is the third iteration. Here cluster center C1 is 3.66 and 9. Cluster center C2's coordinate is 7, 4.33. Cluster center C3's coordinate is 1.5 and 3.5. So after that the new cluster will contain points like A1, A8 and A4. Cluster 2 will contain the points A2 and A7. Cluster 3 will contain the points A3, A5 and A6, and so on. Now some important information related to k-means method. Strength Actually, it is relatively efficient. It takes O(tk) in time, where n is the number of instances, c is the number of clusters, and t is the number of iteration. It is very clear that t will be always very much smaller than number of instances, and it often terminates at a local optimum. The global optimum may be found by using techniques such as simulated annealing or genetic algorithms. So the problems caused by local optimum based termination can be handled by using those techniques. Weakness: it is applicable only when mean is defined. Then it is problematic with clustering categorical data. However, in later case we will use k-mode, a modification of k-means, to handle this problem. And we always need to specify the number of clusters in advance, and it enables to handle the noisy data and outliers. It is not suitable to discover the clusters with non-convex shapes. For example, suppose one cluster is like this. This is one cluster, and another cluster, suppose there is another cluster outside this point. This is a convex type of cluster, concave type of clusters. So this is another cluster. It is very tough to identify both clusters separately by using k-means clustering algorithm, and it is unable to handle the noisy data or outliers. For example, in previous example, suppose one other points exist here, then automatically it will calculate the another mean and capture this noisy point also inside the cluster. Now the next is some variations of k-means method. A few variants of k-mean method which differ in selection of initial k-means, like initial selection of k-means, dissimilarity calculations, strategies to calculate the cluster means. By using these differences, we can optimize the k-means method for better performance. Handling categorical data. To handle the categorical data, for example, some data, their occurrence frequency or like that, we can use the k-mode based features. We replace the mean of clusters with modes using new similarity measures to deal with categorical objects, and by using frequency based method to update the modes of the cluster. A mixture of categorical and numerical data can be handled by using k-prototype method. Next part is hierarchical clustering algorithm. Actually, generally we consider hierarchical clustering algorithms like a bottom-up approach, where we start with the initial set of points or clusters, then join them according to their similarity, and so on. And we continue this process until we get one single cluster. And just opposite to this process is called agglomerative way. The opposite way is start with a single cluster, divide it, and then continue dividing it until we get only one cluster point at leaf nodes. Hierarchical clustering algorithms can be divided into two parts: agglomerative clustering algorithm and divisive clustering algorithm. Agglomerative clustering algorithm starts with each node or point being a single cluster, and eventually all nodes or points belong to the same cluster. For example, here we start with cluster C1 and C2. If both points shows maximum similarity, then we will join both points. Again, we will check similarity with other points, and so on. We continue this merging until we reach some threshold point. For example, our threshold point lies like this. Then just below this threshold point, this will be our cluster 1. This will be the cluster 2, this will be cluster 3, and this will be cluster 4. And so on. Similarly, divisive clustering algorithm starts with all nodes or points belongs to the same cluster, and eventually each node form a cluster of its own. For example, note both agglomerative and divisive clustering algorithm does not require number of clusters k in advance. It uses the termination condition based on some similarity thresholds. Simple algorithm, it is clear from the demonstration that I given. So variations of agglomerative clustering. First is a single link agglomerative clustering. Single link agglomerative clustering, it uses the maximum similarity of pairs. For example, there are so many points like A, B, C, D. Then it first identify the maximum similarity between A and B and then merge them. It checks the maximum similarity between B, C, C, D. Suppose B and C shows maximum similarity, then it will merge them, and so on. But now the problem is it suffers from chaining effect. Suppose A shows maximum similarity with B and B shows maximum similarity with C, then it will merge all 3 points A, B, C as a common cluster. However, in this case, C may not show maximum similarity with A. So this is a chaining effect, and it may create long and thin clusters. And after merging C1, Ci and Cj, the similarity of resulting cluster to another cluster Ck can be calculated as Ci. This is merging, so similarity can be calculated. Suppose we merge A and B, then we calculate the similarity with Cj. Suppose ABC is merged, then we calculate the similarity with cluster D as a similarity with this set of points with this. Not exactly with this and this and this and this and this. Means we will consider this as a combination ABC and Ck as like this. So now again we will calculate the maximum similarity. Suppose there is another merging point like E and F is already available, then we will calculate the similarity with this and this, and so on. And based on maximum similarity, we will merge them. Complete link clustering algorithm. Complete link clustering algorithm uses minimum similarity of pairs. Here similarity between Ci and Cj is equal to minimum similarity between Ci and Cj. X represents the Ci and Y represents Cj. So it makes the tighter or spherical clusters. And after merging Ci and Cj, the similarity of resulting cluster Ck can be calculated. This is same way, slightly different. Means here, suppose there are 2 points A and B and C. Both points are already merged, and this is another point. So we will calculate the minimum similarity with A and C and minimum similarity with B and C. And then again take the minimum of both measures, and based on the minimum of all, we will merge them. But due to the use of minimum similarity of pairs, the system is highly sensitive to outliers. Now the next is group average agglomerative clustering algorithm. It uses average similarity across all pairs within the merged clusters to measure the similarity of two clusters. For example, here we have two clusters C1 and C2. Then to merge them, we will calculate the similarity between these 2 points inside the clusters and all possible points, all possible pairs outside the clusters, and then take the average of them. So this is a formula which represents the average, group average of all points between two clusters that we are going to merge, or for which we are going to calculate the group similarity. Here similarities xy is the count of co-occurring words in x and y. Sorry, for documents we'll check based on the co-occurrence, or we can replace this measure by some other measures also. It does not suffer from the problem of elongated clusters that happens with single link clusters, and reduce the effect of outliers as happens with complete link clustering algorithms. Strength of hierarchical clustering algorithm, it does not require information regarding number of clusters. Any desired number of clusters can be obtained by cutting the dendrogram at a proper level. Not efficient, time complexity is very high. Once decision is made to combine two clusters, it cannot be undone. No objective functions is directly minimized. Now this can be understood like, suppose we start with A and B, C, D, and suppose we merge both them. Now after merging at this level, we realize that this point shows maximum similarity with another new point like this. Then after merging, it is not possible to, suppose this already creates the cluster, then it is not possible to go back and break these cluster points and remerge with these points. So once we take decision, it cannot be undone. So this is a simple algorithm. So we start with a set of input points and check we take best matching as a infinity, then cluster left, cluster right, and for each A, suppose A not equal to B, and suppose we have A, B, C, D, E. Now suppose A not equal to B, suppose we check A and B to taken 2 points, and we have our based similarity measures. Suppose this is the similarity measure between A and B. For this we can calculate one matrix also, A, B, C, D, E, and again now here we will have all the similarity measures. So based on this entry of this matrix, we will select the best similarity matrix. Suppose A and B, here A and B shows the best similarity measures. Then we will convert A and B as a cluster, and then again we will calculate the similarity measures like this in a matrix form and select the best one, and then merge, and we will continue until it supports our thresholds. So this is the same in more programmatic manner. Thanks.